We were discussing the degradation in receiver sensitivity, right, due to external noise sources which are not in the receiver. And specifically, last time we had discussed the finite extinction ratio between bit 0 and bit 1, how that leads to power penalty. So you need certain extra optical power to achieve the same bit error rate in the lead, for example, right? So we discuss a couple more of these sources for degradation of the receiver sensitivity. Okay, so next we look at the relative intensity noise from your transmitter laser source, for example, right? So we discussed about the relative intensity noise when we were discussing semiconductor lasers, right? And we saw that basically the optical power coming out of a laser has some fluctuations, right? So even for constant bias time, the output power is not constant, right? So that would mean that there are some fluctuations in the optical power, right? So let's say for bit 1, we are sending a certain power level, right? So during in the bit duration, that power level is not constant, right? But there's actually some small fluctuations coming from the relative intensity noise of the source, right? And when you detect that, the output photocurrent from the detector, now there'll be an extra noise component, right? Because so now, so imagine your input optical power here now already has some fluctuations, right? Okay. So the noise sources so far we've discussed, we haven't taken any noise in the input optical signal itself. All the noises are coming from the receiver, right? Like short noise, thermal noise, etc. So now, but now you can imagine if there is some noise in the optical signal, of course the output photocurrent will, since the output photocurrent is just responsivity times the incident optical power, the photocurrent will also have this noise. So now if you look at the total variance or the variance in the noise or the variance of the photocurrent here due to noise, so that will have the usual short noise and thermal noise that we have already discussed from the receiver, right? Plus this extra component coming from the rim of the source itself. Okay, and so this rim noise we can write as, so we know that the current is just responsivity times the optical power, right? So the fluctuation in the current due to rim is basically responsivity times the fluctuation in the optical power. So the variance here, you can just write like the fluctuation in the optical power squared times the responsivity squared will give me the variance. Right, so we discussed, for example, that so if we look at the average of the fluctuation, so the average of the delta P is 0 because sometimes you have positive and sometimes you have negative fluctuation. But the average of delta P square is not 0, right? So if you take the square root here, so the RMS noise current due to rim will be the responsivity times the RMS noise optical power. Okay, and this if you can write it like the mean optical power, right? So you have some mean optical power here times a factor Ri, which is basically proportional to the Rin of the laser, right? So from here you can see that so Ri right is basically the RMS noise optical power divided by the mean optical power. And recall our definition of Rin, right? So so if I take the square of this Ri square, so that's the variance of the optical power divided by the mean square optical power. Recall this is how we defined the Rin, right? So if the detector bandwidth is delta F, okay, so if this photodiode has some, depending on the circuitry also in the receiver, if the bandwidth is delta F, then basically the Rin spectrum integrated over the detector bandwidth gives me the total noise. Right, so this is how we have defined the Rin. Right, this was the definition of the Rin. So you can see that basically this Ri factor here is just the area under the Rin spectrum up to the detector bandwidth. Right, that gives me Ri square. Okay, so or in other words, from here you can see that, so this is something, so the signal is proportional to this, right? The denominator is the mean optical power, so that gives me the signal level, and this is giving me the, so this is something like the optical SNR, right? This is 1 over the optical SNR. So this Ri factor is giving me, is just inversely proportional to the optical SNR that I'm getting from my source, right? So a good source will have a very small Ri, right? So we'll see what values of Ri impact our link, but right. So you want a good source will have an ideal source will have Ri equal to 0. Okay, so like typically, if you look at semiconductor laser sources, the optical SNR is typically at least like 20 dB, right? Which means this Ri is typically less than, so 20 dB is 100 in natural units, right? So this is less than like 0.1, 0.01. Okay, so that's the level of Ri we are talking about. That typically, if you take a good single frequency narrow linewidth semiconductor laser in the market nowadays, typically that's the level of this optical SNR due to the Rin noise. Okay, so how does it impact our link? So you can see that the noise current has gone up due to this extra term. Okay, so again, if you look at this Q factor, which is the difference in the currents between bit 0 and 1 divided by the sum of the RMS noise currents. Again, like let's assume like a simple IMDD link. So the current for bit 0 is 0. Okay, and then the noise for bit 0 will just be thermal noise. Right, there will be no short noise because there is no power for bit 0. Also, there will be no Rin noise because the Rin noise you can see is also proportional to the optical power. Okay. Whereas sigma 1 will have all three noises. Okay, so and again, so if we define the average receive power as average of bit 0 and bit 1, and bit 0 has no power, so it's just half of the bit 1 power. then this Q, so in the numerator I have I1, which is responsivity times P1, which I can write as 2 times average received power. And in the denominator for sigma 1, I have all these 3 noise sources. So I'll have, so for example, short noise, okay, then thermal noise, then the rim noise, which is also now proportional to the received power. Okay, so that this whole thing is sigma 1 plus the thermal noise for sigma 0. Okay, so again you can see that, so we have, so on the right hand side it's a function of the average optical power received, which occurs in the numerator and also in the denominator here. So we can try to take the denominator on the other side and then solve for the average optical power. Okay, so if you do that, you get okay, so you get that. So the average optical power that I need to achieve a particular Q, consequently to achieve a particular BER, right, depends on Q like that. And specifically due to rim noise, it has this factor Ri, right, which depends on the rim. So it comes in the denominator like that. Okay, so if you put Ri equal to 0, that's the usual expression we had for the receiver sensitivity just from thermal and short noise. Right, so due to the rim, we get this extra factor. Okay, so now again we can define a power penalty, which is, so for a finite Ri, so for due to rim, we have a finite Ri, and so that increases my power requirement by this factor, right? So the extra power that I require, or the power penalty, due to rim, right? So in dB, I can define like this. So the power at the receiver required for finite value of Ri divided by when Ri is equal to 0 or no rim noise. Okay, so if you put, again, as I said, Ri equal to 0, that you get the standard expression. So this we can write in terms of Ri like this. Okay, so that's the power penalty that we get during noise. Okay, so if you plot this power penalty as a function of Ri or increasing ring, okay. So this is Ri or 1 over the optical SNR on the x-axis. So the curve, so you can see it depends on Q, right? So that depends on the BER that we want the link to operate at. So let's say you want BER 10 to the minus 9, right? Which means Q equal to 6. So for that, this curve goes up like this. Okay, and it really starts shooting up once you start approaching Ri equal to 1 over Q, right? So when Ri is equal to 1 over Q, this factor becomes 1 and then you have 0 in the log. So that shoots up to infinity. Right? So you can see that basically, so the power penalty shoots up for this when the optical SNR approaches Q. Okay, so you can see that typically again, like if you want your power penalty to be less than 1 dB, typically that means that you want this Ri to be sort of less than 0.1 from here, right? Or a received optical SNR of greater than 10 or 10 dB, right? So we just discussed that semiconductor lasers, the state of the art ones, typically have Ri of 0.01, right? So that's much smaller than this. So you might think this, why is this even why are we even considering this? But remember, like for long links, what happens is that you have many amplifiers in between, right? And whenever you amplify the signal, basically what you're doing is you are amplifying the ring noise also. Okay? So at the receiver, the ring noise that you get is not just the ring noise from the transmitter, but through all these amplifiers. Okay? So the received ring noise could be much higher than what is at the transmitter. Okay? So basically, again, the design constraint here is that at the receiver, we want this optical SNR to be greater than 10. Okay, you can see that, yeah, it clearly, I mean, quickly becomes really bad for increasing intensity noise. Okay, so what does this shooting up of the power penalty mean? Means that even if you increase the optical power, keep increasing the optical power to higher and higher values, you will never reach this BER, no matter how high a power you use. That's what this shooting up. Okay, so yeah, I hope it was clear. Any questions on the effect of ring? If not, we'll move on to the next effect, which is timing jitter. Okay, so basically what we are having at the receiver is, right, so we have some bit stream that we are detecting, right, and so for example, you get some I pattern like this, right, there's some 0 level and 1 level, and you want to sample in the middle of the bit period, so this is EB, then you sample at the middle of the bit period where the I opening is maximum, so that you have maximum signal to noise ratio and separation between bit 0 and bit 1. Right, so you set a threshold and then you sample, and if you get the value above the threshold, you decide bit 1, or if you get it below, then you decide bit 0. Right? So you can see that this works well when, or the best when you sample at the instant when the I is open maximum, which happens, you can see obviously at the middle of the bit period, right? So I mean, how you typically do this? You have a clock recovery circuit, right, at the receiver. So from your received data stream, you try to first recover a clock, right, and then using that clock, you try to sample at the middle of the bit period after every bit period. So now you can imagine that if since that the clock you're using, you're also sort of recovering from the received data stream. So the recovered clock can be noisy, right? Which means that, so if you're looking for example, your clock signal, you're looking for some let's say sampling on some, let's say, falling edge of the clock, right? And basically you want this falling edge to line up every time to the middle of the bit period. Right? But again, because the clock is recovered from the received data stream, you can see that because of this noise in the signal, this clock period may not be perfectly constant, right? So basically, for example, let's say here you are in the middle, but in the next bit, maybe you're slightly off from the middle. Okay. Right. So for some other bit, you are slightly off. And how far off? So how far off the trailing edge of the clock is from the center of the bit varies with every bit. Right. Basically, the clock here is noisy, so repetition rate is not fixed, it's varying a little bit because of the noise, because we recovered the clock from the received signal. So basically, there is a random amount by which the sampling time is shifted from the center of the bit, okay, which is what jitter means, right? Jitter means like the sampling instant is not fixed, but jittering about some value. Okay, so this is what we mean by timing jitter, that our sampling instant for every bit is not exactly in the center, but could be shifted slightly by an amount delta t, where delta t is varying from bit to bit. It's some random variable. Okay, so what happens if you're not sampling at the center of the bit? So again, if you look at this, right? So let's say bit 1 the pulse looks like that. Again, so if you're sampling in the middle, you're getting the maximum photocurrent. But now if you're sampling somewhere away from the middle, the photocurrent is slightly lower, right? It reduces your SNR, right? So this can increase your errors. Right, so let's say your threshold is set here. Like you can see that this can take, if you sample at the center, you can take that big of fluctuation without causing an error. But you're not sampling here, the same amount of fluctuation will cause an error because it will take you below the threshold. Okay, so you can see how timing jitter can lead to a power penalty, right? How it can reduce the SNR or increase the bit error rate for a particular received optical power, or if you want to maintain the same bit error rate, you have to increase the optical power received. So there is a power penalty. So the question is since the clock is periodic, the clock jitter will lead to a cumulative effect. So the argument here is that the clock is not perfectly periodic, right? Of course, for any traditional kind of clock source which you get from some oscillator, right? The oscillator has a well-defined frequency of oscillation, which gives an output at that particular frequency, right? But here, because we are recovering the clock from the received bit stream, okay? So if the bit stream, so there is no natural frequency here. There is no oscillator here, or which is defining a natural frequency of operation. The frequency that I get for the clock is derived from my bit stream itself. So now, if the bit stream, you can see, if the bit stream was perfect, right? Basically, I recover the period of the bit stream exactly. But since then the bit stream is not, it is noisy, right? You have dispersion, you have noise added onto the signal. So the recovered clock is not exactly periodic. That's the point. Okay. So the period is shifting up and down randomly by small amounts from bit to bit. Right. So, for example, GOP students, you've done this experiment in the lab, right? With this Manchester encoding and how you recover the clock from the data stream. So now imagine you have some noise imprinted on this encoded data stream that you're receiving, right? So your clock recovery circuit, right? So you're looking for these edges. So this edge will happen when the input voltages reach a certain value, right? That's when the gate will transition to from high to low, for example. Now, if you have noise on your signal, right? When those voltages reach the values required for this transition to happen might vary depending on the noise in the signal, right? So that's why this clock won't be exactly periodic. Okay, so we can define this shift from the center, the sampling time from the center frequency, or center of the bit period, as some random variable, right? So this delta t shift has some probability distribution, which of course can depend on various factors, but typically again, if you have some complicated mechanism that you're not aware of the underlying dynamics, you can typically model the random variable as a Gaussian distribution. Okay, just like most noises we model as Gaussian. Here also we can model this jitter as a Gaussian distribution. Okay, with mean 0, right? So on average, you are sampling at the center, but there are some deviations. So there is a standard deviation tau sub j. So this is the jitter, characteristic jitter time. So this is the standard deviation from the center. Okay. So again, let's consider the IMDD link. And let's consider a pin photodiode, a pin photoreceiver. So working in the thermal noise limit. Just for sort of slight ease of analysis. If you include short noise also, then it's a little bit more complicated. But so for now, let's consider a pin photoreceiver operating in the thermal noise limit. So again, if we define this two parameter, so IMDD again, which means like my bit 0 is giving me 0 photocurrent on average. So in the numerator, I just have I1. But now, so if I1 is like the responsivity times the power in bit 1, where P1, so I1 is like the peak here, right? Because of this timing jitter, only when I sample exactly at the center, I get this I1. But if I have some jitter, then you can see that the value that I get is less than I1, right? No matter if it's a negative fluctuation, if the jitter is negative or positive. I'll always get a value less, or on average get a value less than this peak value. So this value for bit 1 is reduced by some amount here, delta ij, which is the sort of the average reduction in the photocurrent that I get because of this jitter and not sampling at the center, the highest point. Okay. So this is the average reduction in the current, bit 1 current due to timing, right? So you can imagine, so you can appreciate that there will be a reduction, right? Although this process is random and the jitter can be either positive or negative, but even if you have a negative jitter or a positive jitter, you always get a reduction on average in the photocurrent. So that's why you'll have an on average reduction in the photocurrent. Okay, and then divide by the noise. So for bit 1, I have thermal noise plus now an extra noise due to this timing jitter. Okay, so you can see that because of this jitter, right? Let's say there was no noise on the signal. Let's say this was perfectly smooth, right? Then even then, due to jitter, right? Every bit I'm getting a slightly different photocurrent, right? Because I'm sampling at slightly different values, right? So you can see that that looks like a noise, right? Even for a perfect bit stream with no noise, because of jitter, the photocurrent that I'm sampling will be noisy, right? Fluctuating about this I1. So that is this extra noise due to the jitter. So this is the for bit 1, right? And then for bit 0, you just have the thermal noise. Okay. So let's see how we can now estimate. So both this average reduction in the photocurrent and this noise due to the noise current due to the jitter. Okay, so you can imagine to estimate this, we have to assume some shape of the pulse here, right? Because for a given shift, how much reduction I get in the current depends on the shape of the pulse here. So, and recall, like from our discussion on sort of photoreceiver circuits, typically the pulses that we get out look like this, right? So they're maximum in the center. So this is the pulse, photocurrent pulse coming out versus time, right? And then they went to zero. If you go a bit period away from the center on either side, so that the next bit, right, has no interference if you sample at the center. Right, so this was the typical pulse shape that we were getting out after my photo receiver circuit. Okay, and so this maximum is here is I1, right? That's the center here. So this is showing you the pulse shape that I expect without any noise on this. Okay. And now if I move a delta t away, you can see that the current that I'll get will be less than I1. So either here, or positive side or negative side, doesn't matter. So this reduction in the photocurrent due to jitter, delta Ij, will be I1. So if I draw this pulse shape as a normalized one, which has a maximum value 1, then basically if I sample at the center, right, that's when I get I1. But if I don't sample at the center and I sample some delta t away from the center, right? So the reduction in the photocurrent is basically this difference here, right? So H out at 0 minus H out at delta t times I1. I1 is this one to be transferred. Okay, so one can again, so this exact pulse shape that you get again depends on the kinds of photoreceiver circuits and the filter circuits that we use, right? That we had discussed briefly a few classes ago. So one convenient pulse shape to assume is if we assume this to be like a cosine squared. Okay. So that's a reasonable approximation to the pulse shape you get, and it also makes the calculation tractable. Okay, so here, so basically we're getting 1 minus cosine square of pi b delta t, right? Okay. And now, if delta t is small compared to the bit period, which hopefully will be the case, right? Like your clock recovery should at least be good enough that you're somewhere near the center, not near the edge of the or near the transition of the bit. So we can assume this. So we use a cosine approximation here for small values. So into cosine square x or let me go back. So 1 minus cosine square I can write as sine square. Right, and now if this argument is small, which means if delta t is much smaller than 1 over b, then basically I use the approximation of so sine x for small x, I can just approximate as x. So then this delta ij for small amounts of jitter compared to the bit period, I just have the argument here, and so I get okay. So that's the reduction in the photocurrent due to the jitter. Okay, it scales as the square of the timing jitter, delta t square. Okay, so that makes sense again because it should not matter whether delta t is, again we saw whether delta t is positive or negative, I always get a reduction. So that's why there is this delta t square here, right? Delta t, if it's positive or negative, you get a reduction. So question is would there be a square root for IT in sigma? Oh, here you do that. Sorry, the square root is not there, of course. You have the total variance and then you take the square root. Yeah, thank you. Okay, and now so delta t is a randomly varying quantity according to this distribution, right? Which means delta ij is also varying from bit to bit. So what we are interested in is the average value. Okay? So now if we take the average value, so the average value of the reduction in the photocurrent due to timing jitter. So I take the average of this. So I have some constants here. And then I have to take the average of delta t squared. Right? And how do I take the average? I have a probability distribution. So how do I take averages? Right? I just multiply. So this is just integral of delta t square times probability of delta t integrating delta t over the whole range. Right? This delta ij is normal. Oh, okay, sorry. So there is an I1 I missed out here, right? So this is all multiplied by I1. So there is an I1 here. There's an I1 here. Of course, it depends on the level of the photocurrent, right? Because the reduction will be proportional to your signal. Okay, so if you this integral is very easy to carry out, right? For a Gaussian distribution, this is just like the variance, right? So this just comes out to be if I write it in a slightly different form like this. Okay, so this quantity is just the variance tau j squared, right? By definition. Okay, so So I get tau j square here, and I'm just writing it like this, where this quantity is defined as a parameter b. This turns out to be I1 by 2. Okay, this parameter b basically depends on the bit rate multiplied by the standard deviation of my jitter, right? So for a good clock recovery, this value is small, right? You want, so ideal value of tau j is 0. You don't want any deviation, but basically you want this deviation or the jitter to be much smaller than the bit period 1 over b, or b times tau j should be much less than 1, right? Also, so this b parameter is basically a normalized way of characterizing how much jitter you have. Okay, so that's this numerator part here. Now for the denominator, we need to evaluate this noise variance due to the jitter. Okay, and so that's just this now. So you can see, so the sigma j, right? So the variance by definition is just delta ij square, right? So the standard deviation in the noise current into jitter is will be that, right? So again, just like, so we already derived an expression for delta ij. Delta ij square is just square of that. So right. So in other words, this will be, so the constants we'll square and then take square root. So we'll just again get them out as usual. So this will be I1. Right, and then I'll have here an average of delta t to the fourth, and then take square root. Okay, and again I can compute the average of delta t to the fourth same way from this probability distribution. Okay, so you can see that this will come out to be bi1 by square root of 2. Okay, so this here, what you'll get will be something like the standard deviation to the fourth power with some constant here, I don't know, 2 or 4 or something. Right, so in terms of this b parameter, you can see that this comes out to be okay. So now, yeah, so we have expressions for both this delta ij and then sigma j, and both are proportional to I1, the mean photocurrent for bit 1. Okay, so yeah, we can just substitute them here. and then also write I1 as responsivity times P1 or twice responsivity times the average received power for IMDD. Okay, so again we'll have an expression in terms of this average received power here on the right hand side, and I can try to solve it to get E received as a function of the other parameters. So again, if you go ahead and do that, you get this expression for the received power for a particular value of this normalized timing jitter. Here I have okay. So again, if you put B equal to 0, so no jitter, you recover the expression that you have that we had derived previously for a thermal noise limited receiver, right? So then the receiver sensitivity just depends on the thermal noise factor, right? So this is for so similarly now I can define a power penalty due to jitter as the ratio of the receiver sensitivity with some finite value of the jitter divided by the sensitivity for zero jitter. So you can see it's just so then depends on B, this B parameter like this. Right. So B recall was okay. So again, I can try to plot this power penalty as a function of the jitter. So this is the jitter divided by the bit period or the bit rate times the standard deviation of the jitter. Right. So 0.1 means that the jitter is about 10% of the bit period. Okay, so it typically increases slowly up to some point and then shoots up beyond like 15% or so. Okay, and once you reach about 20%, so again, this is for Q equal to 6, corresponding to BR 22 minus 9, right? Because Q is coming here. Okay, so again, if you look at this 1 dB metric, typically, so you want the jitter, normalized jitter to be less than, so you want the standard deviation of the jitter to be less than 10% of the bit period. Okay, which is actually not that bad, right? So you can tolerate jitters up to 10% from the center of the bit. So there is a question: how will we find out this received power if you include both timing jitter and, for example, the relative intensity noise? Then basically you have to include both terms, right? That we separately discussed. So typically, how we look at it is basically we see, okay, we look at it in terms of power penalty for each effect, right? And if you have all cumulative, if you have multiple effects, then you just add up the power penalties and see the cumulative effect, right? So let's say you have a 1 dB power penalty for timing jitter, 1 dB power penalty for the rim noise, 1 dB power penalty for finite extinction ratio due to ISI or something. Then your total power penalty is 3 dB. So you require now twice as much power as what you would have without these effects. Okay. So typically, we look at it in terms of the power penalty, and we add up all the power penalties for the different effects. So if you include other effects, you can imagine there will be additional terms here, right? So there will be like multiplicative terms in the expression for P. So when I take power penalty as this dB, then in the dB they will add up, right? So the power penalties for different terms add up. That's how we look at it. Yeah. Yes. Exactly. So we know what is the power penalty that we get for the different effects, right? And cumulatively, if you want to see, you just add up the power penalties due to all the different effects. Okay, so again, this analysis was for a pin photodetector in the thermal noise limit. But let's say you're using an APD, so you'll also have short noise, which is not negligible, right? So then this expression will become more complicated if you use short noise. So typically then for APD, the curve will be slightly worse, right? So it will be higher like that. Okay. But typically the effect is not that much if you're below 10% of the bit period. Okay. So this metric of if the jitter is below 10% of the bit period works okay for even if you have APDs or when short noise is not. But it's just that it's a little bit higher and it starts shooting up early. Of course, the mathematical analysis will be a bit more complicated. Okay, so yeah, that basically sort of finishes our discussion on optical receivers. So we just end with a couple of plots to show sort of where actual receiver performance, like as measured, lie with respect to these theoretical limits that we sort of discussed. Just to get a feel for, so for example, if you look at the receiver sensitivity, right? So this is the optical power that, the minimum optical power that I need, for example, to get a VER of 10 to the minus 9 of the data rate. Okay, so we had derived this quantum limit, right, which is the best you can do for an ideal photodetector. Okay, so that line lies somewhere here. Okay, so this is the best you can do for an ideal photodetector. Okay, so about, so recall this was like about, so if we define this receiver sensitivity as the number of photons per bit times the photon energy times the bit rate, this was like on average 10. No, 20, right? So the quantum limit was about 20 photons per bit on average. Yeah. Okay, so that's this line. So if you had an ideal detector, we would have this slope, so about minus 70 dBm power for 100 Mbps and about minus 50 dBm power required for 10 Gbps. Right, so minus 50 dBm is like really low power, right? Like 10 nanowatts. Right? So minus 50 dBm is 10 nanowatts. So that's the quantum limit. So let's say at a bit rate of 10 Gbps, if you were at the quantum limit, 10 nanowatts of received power would be enough to get a VER of 10 to the minus 9. If you look at actual receiver performance, the measured numbers, they lie somewhere here. Okay, so I'm just randomly plotting some points here, but you can consider sort of each point as some actual link where the performance was measured. Okay. Typically, they lie like about 20 dB above the quantum limit. Okay, which means actual practical links are operating at about 100 times more optical power received than the ultimate quantum. So basically from here you can see that, so here we are about, let's say, so if you have 20 here, so here we have 2000 photons per bit. Okay, that's where our visual factory receivers operate. Okay, just to give you some idea. So you can think that one way of looking at this is that there is still some room here if we can somehow improve our detection technology to bring this down closer to the. So another way of plotting the performance would be if I look at, for example, the bit error rate as a function of the received power. Right. So this is the sensitivity or the minimum optical power required to achieve a bit error rate of 10 to the minus 9 for varying bit rate. Now here let's fix the bit rate and see how the bit error rate will vary with received optical power. Okay, so 10 to the minus 9 level is here. X-axis is received power in dBm. Okay, so you can see the scale here is sort of around 30 minus 30 dBm. So from here, if you look at 10 Gbps bit rate, then we are talking about points here. So that's like around minus 30 dBm is the range we are talking about. So now we can plot this curve for different link lengths, for example. Okay, so if you have a very short link, so that you don't need, for example, any amplifier in between also. So few kilometers, for example, maximum. So that curve, so there basically you are limited just by receiver noise, right? There are no other noise sources because you don't have any amplifiers in between or any. So in a sense, for a very short link, your sort of power penalty is the minimum. Okay, right? So that's looks like that. Okay, so the BER falls quite steeply with small increases in the received power. Okay, this so 10 to the minus 9 roughly corresponds to about minus 30 from here. Okay, so this is a very short link. So let's say less than 10 kilometers or something. Okay, so now I increase my link lengths. Now if I go to very long lengths with a lot of amplifiers in between, then I'm adding more and more noise, right? So I'm amplifying the rim noise, the optical amplifiers add their own noise. They can lead to intersymbol interference, dispersion over long lengths. So your power penalty adds up. Okay? So power penalty means for the same BER, I require higher power, right? So this curve shifts to the right. So now it looks like that. Okay, and the shift becomes worse and worse. Okay, so this is for example, like 2000 kilometers. Okay, so you can see that up to, so going from very short length to 2000 kilometers, my power penalty is not gone up much. So 2000 kilometers would mean, let's say you have 20 amplifiers every 100 kilometers. Okay, and then once you start going beyond that kind of length, so now smaller increases in length give you more power penalty. Okay, and then at some point, like so, this is like 2600 kilometer, and this curve starts saturating. Okay, so this is something like that power penalty shooting up, right, to infinity, which means so for example, your bit error rate never reaches 10 to the minus 9, even if you keep increasing power. Okay, so this increase that, so this is the power penalty we're talking about. So that much extra power I need to get the same beam. Right, so as I increase the link length, I have some power penalty. So this is in spite of amplifiers along the link. So you're compensated for the fiber loss. So that's not why this power penalty is coming in. This power penalty is coming in because of the noise added. Your signal level is the same because you've added amplifiers in the middle. But you can see that the noise starts becoming really bad once you have more than like 20 amplifiers or so, and then it becomes really hard to increase link lengths much further. We haven't discussed the noise sources due to amplifiers yet, so that will be our next topic, optical amplifiers, and we'll see how they add their own noise also. But typically, these are the kinds of curves you will get for an actual practical link, just to give you an idea of some practical numbers. Okay, so that basically finishes our discussion of optical receivers. Any questions? Okay, so the next topic is optical amplifiers. So maybe we'll just briefly introduce the topic in the remaining 10 minutes or so. Right, so this is the last sort of important component of the optical communication link. So we've discussed transmitters, we've discussed receivers, we've discussed the optical fiber channels. So this is the last remaining important component of that optical communication link are optical amplifiers. Right, and they are the reason why now basically we have global connectivity. So there's a question, can you repeat the explanation why BER cannot become worse beyond a link length? You mean this curve that, right? So you can imagine basically what's happening as we are increasing the link length. Some of these factors, that noise sources that degrade the sensitivity and lead to a power penalty, right? So the power penalty is for a particular BER, we are requiring extra power, right? And beyond some link length, basically this power penalty becomes so large that, right? So recall we had curves for power penalty which were going up like this with some parameter here. Right? So you can imagine these noise parameters scaling with the link length somehow. Okay. So at some point, your link length becomes such that the noise parameter here is at this value where the power penalty is shooting up. Okay, so power penalty shooting up is basically this shifting towards the right a lot. Okay? So that's what we mean by this. So, and we saw that, for example, in some particular instances, at some particular value, this was shooting up to infinity. So if that parameter became that value, then basically you have an infinite power penalty, which means that you cannot achieve that particular beta rate, even if you keep increasing your optical power to infinity. Okay. That's what this means. This happens. It's basically because of this. Okay. Okay, so optical amplifiers are used in various places along the link to boost my signal, right? So of course, for a very long length, you can imagine that the signal is getting attenuated a lot, so I can insert amplifiers periodically, right? So as we've discussed at some previous points in the course, for total link length of L, we could have amplifiers every LA length. Okay, so these are called as inline amplifiers, which are along the fiber optic panel. And so typically this LA is between 50 to 100 kilometers. So typically if your link is beyond 100 kilometers, you would have amplifiers in between every 50 to 100 kilometers or so. Then you could have an amplifier right at the transmitter, okay, to boost sort of the transmitted power. So this is known as a power amplifier or a booster amplifier. Okay, and then you could have one just before your receiver. So integrated. So this one would be integrated with the transmitter. Right. This power booster amplifier will be integrated with your transmitter. Similarly, if you have an amplifier which is integrated with your receiver, this is known as a pre-amplifier because you're pre-amplifying the signal before detection. Okay, so these are the sort of three main types of amplifiers you will see in an optical communication link. Okay, and what is an optical amplifier? We've discussed already optical sources and specifically lasers, right? And you know what laser? A laser was basically a gain medium formed between two reflecting ends, which formed a cavity, right? And we had gain in the middle, right, due to population inversion. So an amplifier is basically a gain medium, right, without this optical cavity. So I'm sending optical power in, then there is gain happening within this medium, and then I'm getting optical power out. There is no cavity, and there is no circulation of the light. You just amplify the optical signal. Okay, so it's basically, you can think of it as a laser without a cavity, right? Or just as a gain medium. And recall how gain medium worked was based on this principle of population inversion, that somehow you get whatever system you have here, you get more atoms, or for semiconductors, more charge carriers in the excited state than the ground state, right? So that the probability of emission is higher than probability of absorption, so that you get net gain. Right? So basically an optical amplifier is a medium which provides gain due to population inversion. Right? And so to achieve population inversion, of course, you need some external energy input, right, which creates this population inversion. And then you have your optical signal coming in, which acquires. Okay, so you have N2 and N1, right, the condition for population inversion. Okay, so P out I can write as some gain factor times P in. Okay, so this amplifier gain typically again is measured in dB. Right. If you look at the field here, right, that acquired some exponential gain. So the propagation equation for the power can be written something like that, where small g is some gain factor. So I can also write this as some e to the GL. Okay, where L is the length of the amplifier. So this capital L is related to, or capital G is related to small g, like so. Capital G is equal to e to the small g. So this small g depends on sort of material properties here, right? Like for example, we discussed it for these 3-5 semiconductors when we were discussing lasers. So typically, this small g, the gain coefficient. So this is known. The capital G is known as the amplifier gain. And the small g is known as the gain coefficient. Right, so units of capital G is unitless, or dB, whereas small g you can see is per length, right? So it has units of per length. So this typically small g, the gain coefficient is a function of frequency or wavelength. Okay, so there will be a bandwidth over which you get this gain. So let's say if this is some maximum value is G0, you can define like a 3 dB bandwidth for this gain coefficient where it goes down to G0 by 2. Okay, so this will be some gain bandwidth delta omega. Okay, so typically you can model this gain curve as somewhat like a Lorentzian function. So this is the frequency omega naught. Of course, the specifics will depend on the kind of system you're using here. So we'll discuss 3 main types of amplifiers, like EDFAs, erbium doped fiber amplifiers, then semiconductor optical amplifiers, which are just the semiconductor devices that we use to make lasers, except we don't have mirrors at the end. And then Raman amplifiers. which work on the Raman effect in optical fibers. So the specifics of this curve again depends on which particular amplifier you're using, but in general, sort of you can model it something like this, along with a dependence on power also. So, okay, so we're saying that it's not just a function of frequency, but also of the optical power. So there is some saturation effect going on. Okay, as you keep increasing the power, the gain, the output just does not keep increasing, but there's something called gain saturation which comes into effect. For high powers, you can see that the gain is going down. Okay, that's because as you increase the power, right, you are increasing the stimulated emission, right, and so the gain coefficient is proportional to the amount of population inversion you have. But as you keep increasing the power, stimulated emission is causing atoms to come down from the excited to the ground state, so it's decreasing the amount of population inversion. Okay, so that effect is basically being captured by this gain saturation. Okay, so this T2 is known as a dipole relaxation time. There's some sort of time constant for which this excited state to ground state transition is happening, and you can see that so this bandwidth is basically inversely proportional to this T2, right? And here this is the gain saturation term. Okay, so this bandwidth here, delta omega g is, you can see 2 over T2. So when it goes down to half, this is the full width at half maximum here is 2 over T2. Or if I look at it in terms of frequency, which is the angular frequency divided by 2 pi, this is 1 over pi times T2. Okay, so let's, for example, if you have a semiconductor optical amplifier, this T2 is about 60 femtosecond. Okay, without going into details about, so there's a question, what is T2? So it's, as the name suggests here, it's a dipole relaxation time. So if you've done any course on basic light matter interaction, so whenever you have an electromagnetic wave interacting with an atomic medium, basically how the coherent interaction of light with matter happens is you form these dipoles, right? So the electric field of the electromagnetic field, the electric field is pulling the electrons from the atoms, right? So there is a dipole created. So the atom forms what is known as an atomic dipole, and this dipole is oscillating at the frequency of the electromagnetic wave, right? So this T2 is basically, so there is a coherent relationship between the phase of my incident electromagnetic wave and the phase of the oscillation of this atomic dipole. Okay, and the time period for which they remain in phase is basically this T2 time. Okay. And after which sort of the dipole becomes out of phase with my incident field, and the interaction is not coherent in some sense anymore. Okay. So that is what this T2 time scale is. Might sound a bit vague if you've not done a basic course on light matter interaction. Okay, so there is something called T1 which you might have heard of, right? So if you take any medium, typically there are two time scales, T1 and T2. T1 is basically the lifetime of this upper state. So if I put an atom in the upper state, how long does it take before it decays? That is T1. And T2 is this dipole relaxation rate, which is basically after what time this atomic dipole goes out of phase with the incident field. And so typically T2 is much smaller than T1, right? So the atomic dipole, so you create this excited state and this dipole is oscillating, right? So this dephasing of the dipole occurs due to some noises in the environment, right? For example, some thermal noise or collision between atoms, okay, some other unwanted background effects. So that causes this dephasing of the dipole much earlier than the actually atom decays down back to the ground. This can be related to refractive index. In some sense, yes, but typically, so this T1 and T2 are important when you are near the resonance, or which means when you're when the energy of the photon is close to this difference between the energy levels, right? So you are close to resonance. Typically, so then basically you have some absorption coefficient which varies sharply with frequency, and also some refractive index which varies very sharply with frequency. So yes, of course, it has an effect on both the absorption coefficient and refractive index. So for example, the width of these are sort of given by inverse of T2, just like this width of the gain curve. But typically the refractive index that we talk about for materials are far away from resonance. So typically you are working somewhere here. Okay. So for example, if you take glass, this resonance transition is happening in the UV range, like some 200 nanometer wavelength. Okay, and we use glass for visible and infrared wavelengths, so our wavelengths are like 800 nanometers or above. So the photon energy is like this. It's far off resonance. Okay, so we're actually not creating this dipole at all. We are like very far away from causing this excitation. So typically, when we talk about the refractive index of materials, we're talking about that in a range which is very far away from resonance, such that there is no absorption, and the refractive index is sort of constant or varies very slightly with wavelength or frequency. Right, so like we saw, for example, when we were discussing dispersion, the refractive index, right, for glass, so over this infrared range was varying like the third or fourth decimal place or something. But now if you go close to the resonance, now you will actually be varying it by units, right? Like so this will actually vary by like of the order of unity. So of the order of the refractive index itself. Anyway, maybe a more detailed answer than what you asked, but yeah. Okay, yeah. So for SOS, this T2 is about 60 femtoseconds. So from here, basically the bandwidth comes out to be about 5 terahertz. Okay, so the gain bandwidth is about 5 terahertz. In terms of wavelength, that comes out to be about 50 nanometer. If you're working at a center wavelength of 1.5 micron. Okay, so that tells you, like, yeah, so if you're working at center wavelength of 50 nanometer, you can get a gain bandwidth of 50 nanometer with a semiconductor optical amplifier. Okay, so for application as an optical amplifier, you want this T2 to be small, right? So that you can amplify a broader range of wavelengths. So for example, if you have some WDM link, then you want to amplify all the wavelength channels simultaneously. You don't want a separate amplifier for each wavelength channel, just from economic cost effectiveness, right? So basically, the broader the bandwidth, the better. Okay, so that's that bandwidth in terms of the gain coefficient. Sometimes the bandwidth is defined in terms of this capital G, the net amplifier gain. Okay, so you can see that. So that is the exponential of this small g. So that bandwidth will actually be much smaller. So if I plot,
sir, class is about to finish, sir. We can extend the time, sir. Otherwise,
yeah. Sorry, I've went over time, but let me just finish quickly. So if I plot the capital G, right? So this is capital G over G naught, or e to the G L over e to the G naught L, and this is small g over G. Okay, because you're taking an exponential now, this will be much narrower. Okay, so if you define the bandwidth in terms of this capital G, right? So if I call that delta omega A, then that is related to this delta omega G like this. Right? Okay, so it depends on the amount of gain you have. Right? So the bandwidth in terms of the capital G depends on the amount of gain you have, whereas the small g is a material constant. It doesn't depend on. So the amplifier gain bandwidth here you can see. So typically G naught will be much bigger than 1, right? 10 or 100 or something. So you can see that delta omega A will be much smaller than delta omega. So, for example, if you want to see in terms of capital G where it goes down by 3 dB from the maximum, right? So that is this delta omega A. That would happen much earlier than the small g goes down by a factor of 2. So if you want, I mean, when you want to use this optical amplifier as a black box, giving you just some amount of gain in dB that you want to use in some part of your link, then probably you're interested in this 3 dB amplifier gain bandwidth, right, which is actually much narrower than your gain coefficient bandwidth. So if you look at it in this terms, instead of 50 nanometer, maybe you can do over 5-10 nanometer.